Hello everyone, and thanks for watching Edupedia World videos. I'm Manish Agrawal, and in this session of atomic structure we'll continue with the discovery of cathode rays and how they led to the discovery of particles that we now know as electrons. Especially we'll focus upon electrons in this topic, okay, and go into the details of properties of electrons as well. So let's start with the discovery of electron. Well, we now know some of the properties of cathode rays, alright, and we saw that how J.J. Thomson demonstrated that cathode rays are actually made up of negatively charged particles. Okay, so even before J.J. Thomson discovered that, other scientists had applied electric fields and magnetic fields to cathode rays, especially magnetic fields, and saw that by the deflection of the direction of cathode rays that they were negatively charged. But what they could not determine was that these rays are actually made up of material particles. Alright, that is something like a solid object. They are actually made up of particles of solid object which are negatively charged. In fact, some of them were thinking that the negative charge and cathode rays might even be separated from each other. Okay, so that is where J.J. Thomson comes into picture, and he proved that negative charge is actually an essential part of the particle itself, and those particles, when in great number, when in significant number, travel from cathode to anode, we see them as cathode rays. Okay, so J.J. Thomson proved that cathode rays are nothing but stream of negatively charged particles. These particles now we know as electrons. Okay, so J.J. Thomson proved that cathode rays are nothing but stream of electrons, okay, traveling from cathode towards anode end. Alright, and in fact he further, to specify and to actually prove that his assumption or his postulate is true, he actually went on to calculate charge and mass of these particles. Alright, so he could not calculate the exact value of charge or mass, okay, but what he did accurately calculate was ratio of charge and mass. Okay, let's say charge is represented by small e and mass of those particles which constitute cathode rays is represented by small m. So he calculated this ratio, okay, that is charge to mass ratio of those particles. Okay, this ratio is also called specific charge ratio. So let's see how he did that. Okay, how he calculated this ratio and how this ratio actually signifies that these cathode rays are made up of material particles which have negative charge as their inherent property. Okay, so he performed a series of experiments with the help of other scientists in his team, and in a crude way we can represent his experiment by this diagram which you can now see. Alright, so this end here, okay, this end is again cathode and this end is again anode. Alright, so now we know that from this end, from cathode towards anode, stream of particles are going to move. Okay, when we apply a high voltage here, okay, a high voltage here, a stream of particles are going to move. Now what he did was he extended the tube further. Okay, even after anode he further extended the tube, and at this end he had some kind of photographic screen or plate. Okay, again you can just say that it is a plate coated with some material like zinc sulfide, alright, some fluorescent material. So due to their high velocity, as they travel from cathode to anode, these particles are not going to stop at anode. Okay, they are going to overshoot. Alright, they are going to overshoot anode and go towards this end. Alright, they are going to move towards this end to the screen that we have coated with fluorescent material. Okay, so now this section after anode, this section of experiment becomes important. See, in this section what he did was, first he applied an electric field here. Okay, so this is the positive end and this is the negative end. Alright, he applied an electric field. Okay, so this is again anode here, this is anode, and this is cathode. Okay, forget about gas or anything over here. Okay, this electric field is applied outside the discharge tube. Okay, in such a manner that electrodes are present outside the discharge tube, but their electric field can pass through here. Alright, so obviously what he saw was there was deflection of these rays towards anode. Okay, so now a little bit of physics comes over here again. See, they have a velocity in this forward direction towards the screen, and now at the same moment they are trying to move towards anode as well. Alright, that is towards upward direction. So they have a velocity in forward direction and another velocity towards upward direction. Okay, so in essence what happens is cathode rays end up moving something like this. Okay, so they get deflected towards this end, and here we see flashes of light. Okay, and by the flashes and making some more experiments and calculations, you can calculate exact value of this deflection. Alright, see, this was going to be their initial path. Let's say this was going to be the initial path. If there is a hole here or thin plate here, the cathode particles will overshoot from here and strike at this part. But now since you applied an electric field, it will deflect towards positive end, and you can calculate exact value of this deflection. That's what he did. Okay, let's call this, say, something like phi. Okay, so this is the deflection caused by electric field. Alright, let's call it phi. Then what he did was, okay, after applying electric field, let's say he removed that electric field, and now instead of electric field he applied a magnetic field. This is the north pole. Okay, this is the north pole, this N, and this S is the south pole of, let's say, a magnet. So there is a magnetic field over here, okay, in between north and south pole. Now another thing that you are going to study in physics in your class 12th is that charge particles, any charge particle, whether positive or negative, just like it gets deflected by electric field, it also gets deflected by magnetic field in some way. Okay, so what he observed was, even in presence of magnetic field, these cathode rays got deflected. Okay, so he arranged his magnetic field in such a way, that is, he arranged north and south polarities in such a way that these cathode rays now got deflected in the downward direction. Alright, that is opposite to the deflection which was observed due to electric field. Okay, how that deflection occurs? What is the, basically a deflection is caused due to some presence of some force over there. Okay, so there is some force due to interaction of magnetic field with the charged particle. What is that force? What is the value? You don't have to go into that. Alright, you will study that in class 12 in physics. Okay, but here just we need to know that there was some deflection. Let's call that deflection theta. Okay, let's call that deflection theta. Alright, so now he was able to calculate deflection due to electric field phi and deflection due to magnetic field theta. This deflection due to magnetic field was quite significant. Alright, because before him other scientists were not able to observe significant deflection in presence of magnetic field. Okay, so now when he applied these simultaneously, both electric and magnetic field is going to make the cathode rays deflect upwards, and magnetic field is going to make them deflect downwards. Okay, move downwards. So he adjusted the values of these forces, electric and magnetic forces, such that the deflection due to, say, both is equal in magnitude but opposite in direction. So one pulls it upward, one pulls it downwards, but with same force. So what is going to happen? The electron is going to strike over here. Okay, that is at the center, because both deflections counteract each other. So at this point he can say that, okay, at this point he could say that deflection due to electric field is equal to deflection due to magnetic field. Alright, now by using the formulas for this deflection, okay, equating them, okay, using the formula which you don't have to study here, alright, he was able to calculate charge to mass ratio. Alright, he knew the magnetic force that he was applying here because he was the one who used the magnet. He also knew the electric field present here because he was the one to supply the electricity. So he knew the values of forces and he could calculate the values of deflections. So using this equation, he came up with this number, charge to mass ratio. Alright, and he calculated that this value is equal to, in magnitude. Alright, in magnitude, let's forget that the electron is negatively charged. If we just want to calculate magnitude without positive or negative sign, he calculated that this ratio comes out to be 1.76 multiplied with 10 to the power 11 coulomb per kilogram per kg. Okay, so this C represents coulomb, COULUMB. Alright, coulomb, if you remember, is unit of charge. That is how charge is calculated in SI units, coulombs, and kilogram is unit of mass. So unit of specific charge ratio, this charge to mass ratio will be coulomb per kg, C per kg. Alright, and its magnitude is 1.76 multiplied with 10 to the power 11, and this is what he calculated. And for this study and for this calculation, and as well as his further studies in electrical conduction in gases, he actually got a Nobel Prize later on, but that Nobel Prize was in physics, not in chemistry. Alright, again, in fact, this whole topic is going to be part of something that you might come to know as quantum physics. Alright, even in nuclear physics you are going to study some of electrons and subatomic particles. Okay, even in chemistry we study them, but basically they are something that we now know as quantum physics. Alright, so he got a Nobel Prize in physics for this, and now you know what he did actually, what he performed in that experiment. Okay, so now we know that cathode rays are nothing but stream of negatively charged particles called electron, and we also know the value of their charge to mass ratio. Okay, so let's move on to electron and some of the properties of electron that we need to remember. Okay, so first, what is electron? Well, we now already know it is a negatively charged particle. Okay, what you need to know is how it is represented. It's often represented as, okay, small letter e with a superscript of negative charge. Okay, so E minus, so this represents an electron. Okay, it is just a way of representation in symbolic terms. Okay, it is also represented in this way. This is beta particle, symbol is called beta with a negative charge, represents electron. Alright, this symbol is actually what you often use in nuclear physics. Okay, nuclear physics and nuclear chemistry, electron are often referred to as beta particles. Okay, they are often referred to as beta particles. Beta particles are nothing but electrons essentially. Alright, and they are represented by symbol beta minus instead of E minus. Okay, so E minus or beta minus basically represents electron. Right. Second point, they are elementary particles. That is to say, they are fundamental to everything. Alright, elementary particles means these particles are or cannot be further divided into constituents or subparts. Okay, even today we have not been able to establish how electrons are formed, basically what constitutes electrons. We just know that they are elementary particles because they form everything, but they are not formed by anything that we know of. Alright, so they are elementary particles. Okay, let's go on to some further important properties of electron. First property that you need to know is their specific charge ratio. Okay, this is what Thomson calculated, we now know, and it is represented in symbolic terms as E by M. Alright, E is often used, okay, E is often used as a symbol for charge. So when I write E minus, I mean electron. Okay, but E means charge and M is mass, so E by M ratio is actually called specific charge ratio. Alright, so this specific term is actually, you are going to come across it quite often in your studies. For example, you might come across specific volume. So specific volume means volume divided by mass. Alright, So this specific quantity is going to be quite common. Alright, so specific charge means charge divided by mass. Okay, and its value, if you take the sign that charge of electron is negative, then it comes out to be minus 1.76 multiplied with 10 to the power 11 coulomb per kilogram. Okay, so it's quite high. Alright, it's quite high. 10 to the power 11. This C is for coulomb and coulomb per kg is the unit. You have to remember this value. Minus 1.76 multiplied with 10 to the power 11 coulomb per kg. Okay, you have to remember it for your exams. Next property, value of charge. Now this value of charge, okay, J.J. Thomson calculated the exact value of specific charge. Okay, specific charge ratio he had calculated, but he was not the one who actually calculated the exact value for charge. He did some calculations for the mass, okay, and approximately he got a value of mass which was not accurate, okay, or right, but value of charge was actually later calculated by another scientist called R.A. Millikan, alright, using his oil drop experiment. In the next session we are actually going to look into this experiment of R.A. Millikan and how he calculated value of charge. Okay, and he calculated it and found that value of charge is minus 1.6 multiplied with 10 to the power minus 19 coulomb. Okay, so that is quite low, very low. Alright, so this value again you have to remember this value. Okay, so this is coulomb. Coulomb is in SI unit. Okay, in SI units, this is the value of charge on an electron, on a single electron. Okay, it is also equal to minus 4.8 into 10 to the power minus 10 ESU. ESU is electrostatic units. Okay, ESU is electrostatic units, that is in CGS. Okay, so you can either calculate the value in SI unit or you can calculate the value in CGS unit. Again, either you should know the conversion between 1 coulomb and 1 ESU, or you will have to remember both these values. Okay, if you know the conversion between coulomb to ESU, that is electrostatic units, you can simply remember the value in coulomb and then convert it whenever required. You won't really need to use ESU units very often, but coulomb value of electrons charge you have to remember again. It's going to be very important and very essential. It might not be given in your questions. You will have to remember and use it wherever required. Alright, now as we saw, electron is basically an elementary particle, that is it is a fundamental particle. So charge on an electron is actually the lowest value of charge that we know of. Alright, so if you have 3 particles, or say even one big particle with great amount of charge, then the value of that charge is always going to be some multiple of this value. Okay, this is the most fundamental value of charge that we know of. That is why charge on one electron is also referred to as 1 unit charge. Okay. So if I have 2 electrons, I can simply say I have 2 units of charge, or if I have 3, I can say 3 units of charge. There is nothing like 2.5 unit of charge, because there is nothing like 2.5 electron. Electrons cannot be divided, as we now know. Alright, so any value of charge in the world is always going to be some integral multiple, alright, of this value 1.6 multiplied with 10 to the power minus 19 coulombs. Okay, so lastly, now if you know value of charge, okay, as Millikan calculated, and we already know value of E by M, so we can simply very easily calculate M. Alright, we know that this value is equal to E by M. Now we substitute value of E as minus 1.6 multiplied with 10 to the power minus 19 coulomb here. Okay, we substitute this value and we can simply solve this equation to get exact value of mass. Right, so now we also know how to calculate mass of electron, and this value comes out to be 9.1 multiplied with 10 to the power minus 31 kilogram. Okay, again this is in SI units. It's 9.1 into 10 to the power minus 31 kilogram, and again you will have to remember this value. Okay, there is no going around it, you will have to mug it up. Okay, so we have represented mass of electron here as M with subscript E, just to be specific that we are referring to mass of an electron over here. So in CGS unit, okay, CGS of mass is grams, so this will come out to be 9.1 multiplied with 10 to the power minus 27 gram. Alright, in CGS unit this is going to be the value. Okay, because 1 kilogram is 1000 grams, so you multiply this value by 1000, you get it in CGS units. Alright, so now you can answer that value of mass is this, value of charge is this, and specific charge ratio, even if you don't remember, you can simply calculate it using the ratio of E and M. Alright, if you remember these two values, you can easily calculate the value of E by M, and you don't have to remember it. Alright, but these two values you have to remember. Okay, and now you see why the value of specific charge was so high, 10 to the power 11. Why? Though the charge was low, 10 to the power minus 19, order of 10 to the power minus 19, but mass was even lower, of the order of 10 to the power minus 31. Right, so given that mass of electron is so low, we can see why specific charge ratio is so high. Alright, so lastly, this deals with the part of electron that we need to know over here. Alright, but lastly, just one important note, charge on 1 mole electron is called 1 farad. Alright, you need to remember this again because it's going to be important later on. So let's see it over here. Charge on 1 mole electron. See, I know the charge on 1 electron is 1.6 multiplied with 10 to the power minus 19 coulomb. Alright, so what will be charge on 1 mole electron? It will be Na, that is 1 mole Avogadro's number multiplied with charge on 1 electron, that is 1.6. Okay, we are just talking about magnitude here, 19 coulomb, and Na is 6.022 multiplied with 10 to the power 23. So when we multiply Avogadro's number with this charge, we get total charge on 1 mole electrons. Alright, and this value approximately, you don't have to remember the exact value, but approximate value is 96500 coulombs. Alright, you have to remember this value so that you know 1 farad. Okay, farad is nothing but another way of saying I have 1 mole electronic charge. Okay, so I have 1 farad charge, that is I have 96500 coulomb of charge. So 1 farad is 96500 coulomb. Alright, so you have to remember this. Farad is represented simply by capital F of 1. So 1F is equal to 96500 C. Okay, so that done us with electron. Okay, let's revisit discharge tube again. Okay, let's see what was going on over there that electrons were formed. See very quickly now, because we already know how discharge tubes work. Okay, so this is a discharge tube. I have cathode here and have anode. Let's say my cathode and anode are made up of very thin material. Okay, very thin metal foils. Even if this metal foil is not perforated, that is, even if it does not have holes, we can still see some of the cathode rays, that is electrons, coming over here. Okay, that is, we can still see flashes of light over here. Okay, on our ZNS zinc sulfide screen. Why? Because cathode rays can pass through thin metallic foils. Alright, so this is another property of cathode ray that you might want to remember, that they can pass through very thin, okay, very thin metal foils. Okay, there are also other properties that we don't have to go into detail of. One, we already now know that cathode rays are affected by electric and magnetic fields. Okay, and there are more, like they affect photographic plates. Okay, they can also be used to generate X-rays. Okay, there are many other properties, we do not have to go into them. Alright, we just need to see what was happening in discharge tube. See, before what happened, before the amount of gas inside the discharge tube was very high. That is why they were able to observe some discharge, but they were not able to observe specific cathode rays traveling from cathode end to anode end. Alright, only when amount of gas was reduced sufficiently were they able to observe cathode rays, and only when voltage was sufficiently high. Why? See how cathode rays are generated. If you know that, you can understand why. Cathode rays, now we know, are nothing but made up of electrons, stream of electrons flowing from or traveling from one end to another end. So how these electrons are generated? Okay, it means due to high voltage and low pressure, some electrons were generated and these electrons now traveled. So how the electrons were generated? Well, actually the source of electrons are two over here, two different sources. One source is the cathode itself. Okay, one source is cathode itself. Okay, current, as you might know or you will know in your class 12th physics, current is nothing but flow of electrons. Sorry, this is negative end and this is positive end. So current is actually flowing here and electrons are actually flowing here, you can say. Right, so one source of electron is here. So applying sufficiently high voltage ensures that there are electrons here which can leave the cathode end and move towards anode. Okay, other and more important source of electron is the gas inside the discharge tube. See, let's say I have taken air over here. Okay, I have taken air in this tube. Alright, so even the air that you are now breathing always have some ionized particles. Ionized particles, that is cation, anion. Okay, you might know from your class 9 studies. For example, Na positive is an ionized particle, H positive, alright, or say He positive. These are all ionized particles, or Cl negative. Okay, so gases always have some ionized particles in them. Even one or two might be enough. Why? Because now I have ionized particles here and I am applying sufficiently high voltage. So that is, there is sufficiently high electric field between these two electrodes. So due to that electric field, these ionized particles gain high velocities. Alright, and when they travel in presence of these high velocities, they will either move towards this end or this end. Basically they will move. Okay, so when they move, they might get obstructed by another gaseous particle. Okay, let's say H. Okay, so let's say H. Now this H, when gets knocked by another particle, subatomic particle or an atom, it can lead to its own ionization. Right? That is due to getting struck by high velocity particles. Now this atom again gets ionized, and ionization of this has led to formation or basically presence of another electron in our tube. Now even this electron will start moving towards, even this electron that comes from here will start moving towards our anode. Alright, so this happens only when the particles have high enough velocity to knock an electron out of another atom. Okay, and to gain that high velocity there must be empty space over here. If there are a lot of obstructions over here, they will never be able to gain so high velocities that they can knock out another electron from an atom, or they can travel from cathode to anode. Okay, they will get obstructed over here somewhere in the between, and your discharge will end over here. Right, so that's why we had to reduce the amount of gas inside the discharge tube, and that is why only at very low pressures we were able to observe cathode rays traveling in straight lines. Alright, so electrons come from cathode, okay, or you can say they come from application of high voltage leading to ionization of gases. Okay, high voltage can also ionize gases even if some ionized particles are not already present. Alright, so high voltage leads to ionization and low pressure leads to further ionization and smooth traveling of electrons from one end to another end, hence forming discharge tube experiment leading to cathode rays. Alright, so this is what you need to know, and from this how cathode rays were formed, how electrons were traveling, now you can better understand how and when they were observed and why they were not observed before. Alright, so in the next session we'll deal with the Millikan's experiment on calculation of electron, charge on electron, and that is it. So until next time, and once again thanks for watching Edupedia World videos.